Uh-huh. Okay. So hello everyone. I'm Chiro, founder of Origin Network and also CDO. Today I'm talking about like recursive proof with Plonky2. Actually, like we want to make like a demo and also the presentation about Plonky3, but then there lack of document and other stuff, so we can introduce it right now. So we just go to the recursive proof with Plonky2. So I think like right now, like we see a lot of run-up project, and if we think about run-up, like we have a lot of transaction and how we can prove it with on the other chain. So the basic concept is you have a lot of transaction, and then you're going to bundling them to one single proof and verify it with smart contract on the different chain. So it's quite like basic with run-up. But then to make the run-up like go efficiently, like we need to do something like if we can do something like we can generate a proof for transaction 1, and then we generate proof for transaction 2, and then we generate proof for transaction 3, and then at the last we will have one single proof that can verify efficiently from the other chain. But I think like for this model, actually like people can have something like similar to IVC. For example, they're going to create proof one single state, and then going to include the previous proof to this state and also prove it. For example, like Kimchi, they utilize this, and they actually like snack-based IVC. So there are different ways to achieve this, but then today we're going to talk about Plonky2 and how they can actually like make it more efficient and faster if you compare with other proof. Okay, so a little bit about the background. Actually, Origin Network is the R&D company in Vietnam, and we focus on zero knowledge proof. IVC, for example, like we have one paper, it's called ramen pasta. It's actually like folding scheme, but then you combine with like it can provide the hiding, and also can provide the ability to not rely on the not breaking the random oracle model. So I think like we're going to have the implement for ramen pasta as well. Besides that, we also focus on data integrity and hope that we can provide the zero knowledge proof for every state of data. That's why we focus on build up something like ZK data run-up, verifiable data pipeline. And I think like another step in cryptography that we enjoy to get in. Okay, and so let's talk about like Plonky3. Like actually, like what is Plonky3? It is utilize the Fry-based polynomial commitment scheme, and also combined with tuple Plonk and also small field. So it's not the closed one, but then I think it's simplest definition, so people can know like how it's going to work. For example, if the Fries is based on the hash-based commitment scheme, and actually like just like the other, like every Fry base, it do not need the trusted setup, or it can do computation on small field and make it very efficient for computer. And also like tuple Plonk, it's a Plonk, and they can add like custom gate into it, so they can actually like write the verifier with the tuple Plonk, and also make it very easier for people to actually do recursion with Plonky2. My team actually like have different approach. Like we try the product with Kimchi, and also Hello2, the PSC version. And we also try with another one is Nova. And the last we try is Plonky. And then possible 3 in the future. Actually, like we already tried several kind of recursion proof and try to do it. With Kimchi, I think like the problem is the IPA and also IVC, IVC snark is very expensive. For Halo 2 of PSE, actually like this version of Halo 2, like I think like we cannot like do the recursion with the like the Mercury. We cannot prove the Mercury or do ZK data run up with the Halo 2 very efficiently. So we just have several candidates for it. So for Nova, actually like it uses like folding scheme, and is the recursion on Nova protocol actually like very cheap, but then we found is not as good as we expect from the paper. Like the result, it's quite slow on small circuit. Like as long as you don't have the circuit big enough, you cannot receive any benefit from Nova. And then we come up with the last option. So Plonky2, actually like they have a lot of stuff that help people to build the recursion really fast if you compare to 3 other candidates. And then let's see. Okay, what we have here, like efficient like 64 bits Goldilocks field. I think like this quite a good approach. Like right now, like we have a lot of AMD 64, and actually like this field going to work very natively on your device very natively. So every computation is like much more faster if you use the bigger field, and then no shortage setup because it's based on Fry, and also like post quantum safe. And just like I say, TurboPlonk help people to build the verifier inside the circuits. So you're going to create something like this. You're going to have the circuit that also verify its own result. So you can repeat it. Like for example, like you're going to repeat the block, and the given circuits can also like verify the result of previous step. Yeah, and then the configurable fry param, and what it is. So actually, like we have something like configurable, like they go is raised. It the 2 to the row, and then they're going to estimate the security bit based on row time number of query plus writing. So actually, like we can adjust it. Like if you do a lot of query on the commitment scheme, the proof size will be big. Big proof size, increase big proof size. And if you're going to increase this, it's going to be the, if you increase this, it's going to be the slow proving time. So actually like Fries and Plonky2 allow you to configure it. For example, like you can set the rate 2, and then you have to do many more query on the Merkle tree proof. But then you can do fast computation, like fast proving, and then the proof size is really big. So people can actually like have the choose between the trade-off. They can choose to be have the fast proof generation, or they can choose to have very short proof. Depend on this configuration. And actually, like this field selection have a lot of advantages. For example, like this is the Goldilocks field, and then its structure is quite simple. And then it also provides the methods allow you to do some engineering engineering trick to actually like reduce the cost for computation. For example, here, like we can write in this way, and also we can rewrite the bigger value by compute this, and the result is quite easy to understand, and also you can reduce a lot of computation with this. And I think like they're going to implement in the code of Plonky2 to reduce the cost of computation. Okay, then this one also use the same technique. So actually, like it quite the same when you build the circuits with any Plonk-based proof system. Like actually, like we will have something like we actually like define something look like a table. Like we will have the table, and we have row and column. And then people going to write this constraint in this table to make sure that the result, and then also make sure that the value going to constraint, and each row going to constraint together, or maybe like they can have the copy constraint between like two different rows in Plonk. So I think it's quite similar if you already like familiar with Halo 2 and also any Plonky's proof system. And then what will make it different? So let's go back to the problem with the run-up stuff. Like we have this one, this 2, and also this 3, and also this 4. Like how people actually like can make it more efficient. They're going to generate the proof here, but then the configuration, like they're going to set the configuration to the row going to be like equal to 1, and then they're going to have the so actually like the rate is 2 right now, and then they do a lot of query to guarantee that the proving process is really quick. And this day, so we have pi 2 here, and pi 1, pi 2, and actually the proof is really big on this step. But then when people create another proof from the previous step, they're going to increase this row number. Then they're going to include row, and then right now like we will have like very small proof, plus slow computation. So actually, like with this approach, like you can do everything in parallel. For example, like you're going to generate the proof for test 1 and test 2 and also test 3 or test 4, and then you can prove it really quick, and eventually you can generate a very small proof to put it on chain. So it is very different if you compare to the other approach, like for the other proof system like Kimchi, you're going to create one proof, and then you create another proof that include it. So everything have to happen in sequence. So you cannot do everything in parallel. So Plonky2 provide the people the way you can do everything in parallel. And you're going to describe something it called the inner circuit and then the outer circuit. So the inner circuit, you're going to verify very small proof here. And the outer circuit, we're going to prove the correctness of every inner circuit, or the proof of inner circuit.
So the inner circuit has to be small, so the outer circuit can include a verifier of the inner circuit, no?
Actually, like when we have this inner circuit, it is not necessary to be very small, but actually, like we want to, if you have the smaller circuits, apparently it will be faster. Like everything it depends on the circuit size. But then when you like write the circuits, like everything like will have the baseline that you cannot sing it like make it louder than that baseline. So
I mean like the proof size, no? The proof size of the inner circuit has to be small.
No. In the approach of Plonky, they actually like trade off, like they want the proof generate in this step, it's going to be very very big.
Oh.
But then what they receive from this, actually like they're going to create another proof from this one. But then the verification step for this proof is really quick. So because they also like this here, this step, you're going to be verify it, but not actually like prove it. Actually, the thing you do is you're going to prove the verifier. Like let's say I have let's say I have P1 and V1, and here I have P and V, like prover and verifier. But this step, you're going to prove the verifier 1 result. So actually, like, is not depend on the size of this circuit, but then you can have like grab it and rewrite the prover, the verifier, to be a circuit. So it not depend on the size of previous one.
So the outer circuit contains a verifier.
Yeah.
No?
Like it's going to be like you will have something like that. It also include the periods verifier for periods, so you can input the proof here as well. And then we have another proof. Maybe no. Maybe like this is the proof of the outer one. But then you also able to continue to recursive this proof in the same way. So that's why like people going to say something like we write the circuits and it also include the verifier for it. So that's how they going to do the recursion. And here actually like we can do a lot of step of recursion in not like you actually like also able to do recursion on this proof as well, as long as you have the verifier for it, so it's gonna work. Okay. Right now, like we try to do something like it's called the ZK data rollup. Like when you have the database and then you also want to prove every data like input and output going to be correct. So we have one commitment scheme, and then the thing to do is we have to prove every transaction on the database, going to transform the Merkle rows from rows to rows prime. I think like this is like very trivial problem.
Can you change the amount?
Okay, thank you. I think it's very trivial problem, and then when people come up with the recursion, the biggest problem is how we can reduce the proving time, like make the cost more efficient. Like right now, like we want to maybe hit the 10,000 update on the database, but then it's really difficult. Like the proving time and also how we going to can generate like the proof for 1,000 update. Like we have to do everything in parallel, and then going to create one recursion proof at the last. So there are a lot of things need to be done. For example, like the first thing we're going to from our implementation. So like to do the parallelization for it, like we're going to have the pre-compute step. So this pre-compute step going to generate the Merkle proof for 1,000 update, and then we're going to generate multiple parallels threads to compute the proof, and also include this proof in the final proof. So it can make everything much more efficient and also reduce the cost to generate the proof. Okay. Here is the idea of what we're going to show you in the next slide. Like we're going to generate the proof and also generate the outer proof that can be verifiable on chain. Okay. Oh. Okay. I will do the demo right now. Actually, like it's very simple demo. Like we do recursion on the Merkle tree, but like right now, like it's not so efficient. So we need to a lot of things need to improve here. Especially like we can. So what we're going to do in this sample, like the first thing in this sample, we're going to update the spare Merkle tree. Like as you see here, like we have one spare Merkle tree here, and we're going to update it with the data, and then we're going to verify the Merkle witness, and then prove the transformation of current rows to the new target Merkle proof. And then we have to done the verification. And also, like this pass, it's because like for the Plonky2 actually I use the small field, so you have to set like every limb of the small field to the target's value. That's why like you see like we have to copy each field into it. And then we're going to verify the Merkle witness here. And then after that, this step, we're going to update like the inner builder. And then the last step, we do the recursion for the proof and have the final proof. So we do everything following this step. The first one, update the SMT and also the data. So get the Merkle witness. And then we're going to prove the transformation of the root to the root prime. So and then this step happen in the inner proof, inner circuit. And then the other step is going to prove the included and then prove this inner proof. No, actually, like it's going to prove inner proof. And that's all. So actually, like, right now, like we got a lot of time to actually like generate the given proof. And recently, like my team focused on Plonky2 as well. And then the biggest problem with it right now, like it actually even like Polygon said that it already production ready, but right now like when you try to rewrite it or build any kind of recursion on it, it's not possible right now. Like the whole Plonky2 not actually like complete yet, so it's very painful. And some people come up with the idea like with Plonky 2.5, and it actually like has recursion. Like they're going to use the Plonky3 primitive, and then combine with the Plonky2 recursion. So it's quite a mess, but then that is the best that we have right now. And also like Plonky3 is more look like ZK stack. Actually like Plonky2 we have tuple plunk and also the tuple plunk and fries, but then Plonky3 it replaced with air and fry. So it must look like much more look like the ZK stack. And another project from Polygon is the Starkey, and now Plonky3 look like Starkey. Okay, like we call a lot of time to just do like city 4